Here we see the formula for empirical probability. P hat stands for the empirical proportion or empirical probability of X successes in N trials. A P without a hat, on the other hand, is actually reserved for the true proportion or true probability of success. In some cases, we can theoretically calculate that true probability P, but in many other circumstances, we'll never know what the true proportion P is. And instead, we have to use P hat as the best estimate of the true proportion. So, in the example I have below, we'll actually know what the true probability is. The example involves a casino game. And let's say it's a game where the computer programmers who had made the game, they know what the true probability of success is. It's 0.4. Now John, a gambling addict, is going to keep a record of how he does in this casino game. It's a simple game where he bets on a color, and if he wins, he'll get $1, but if he loses, he has to pay $1. Since the probability of success is less than 0.5, he's actually going to lose more times than he's going to win on average over the long run. And we want to calculate what his expected value would be over the long run, because that's one way to tell whether the game is a good one to play or not. So, okay, he's got a 0.4 chance of a win, and he'll get $1 in that case. A 0.6 chance of a loss, and he'll lose $1 in that case. It comes out to a negative 20 cents per play on average. So that's one indicator that it is not a good game for him to play. If it came out 0, it would have been fair. It would have been a fair game, and he would have broken even. Since it comes out negative, it means over the long run, he's going to tend to lose on a play. But that means the casino is going to win on a play, on average. So let's take a look at his graph that he made. The theoretical probability is 0.4. At the start, it looks like he was doing well. He started off with a win because he had a high empirical probability. And then as time went on, we see that his cumulative empirical probability started to trend toward the theoretical probability according to the law of large numbers. And that's expected. So in these next examples, we'll see why it's actually a bad game for John to play. Let's start off with analyzing how he did after 12 plays. So the number of plays is the horizontal axis here. You want to find 12 and then just trace it up until you get to the cumulative curve. And trace that over and see what empirical probability he'd had at that time. Looks like 0.6. Now we want to use the formula for empirical probability. P hat equals X over N. We can actually rearrange it through algebra. X equals N times P hat. The reason I did that is that we know the number of trials here. It's 12. And we know his cumulative empirical probability from the graph. This is P hat, whereas this is P, the theoretical probability. Okay, so 0.6 goes here. In this way, we'll find out how many times he had won out of those 12 trials. Approximately 7.2 wins. Which means that he'll have 12 minus 7.2 equals 4.8 losses. So we actually want to subtract them because he gets $1 every time he wins, and he pays $1 every time he loses. So his net gain here is $2.40. So he's actually ahead. He's doing well at that time. What about after 26 plays, though? Trace it over to see what his cumulative empirical probability is. I estimate maybe 0.32. So we'll use the formula. 26 plays, cumulative empirical probability of 0.32. He's got approximately 8.32 wins. And we could say 26 minus 8.32. See how many losses. 17.68 losses. All right, so his net gain is going to be 832 minus 17.68. Now he's at a negative 936. Not doing so well anymore. Now he's in the hole. So didn't go well between 12 and 26 plays for him. Now let's try it after 60 plays. As you can see from the graph, at this time the cumulative empirical probability pretty much equals the true theoretical probability. Because there have been so many plays, it's expected that they should be really close at this time. For that reason, when we do our calculation, we could just use P, which is the expected probability of success. So 60 plays, 0.4. Let's see how many wins. 24 wins. And 60 minus 24 equals 36 losses. We want to subtract them too. $24 in revenue, $36 in expenses. Now he's down to $12 in the hole. Not too bad for a day. Could be worse. But what if he were to keep playing? Should he keep playing? Well, after 60 bets were placed, we see that John had actually lost more bets than he won. Now, what if he were to go farther and play 10,000 times? It's conceivable that he could over his whole lifetime, perhaps. What would the calculation look like then? Well, if he plays 10,000 more times, then we might as well assume that the p hat is P, because that is a huge number of trials. It would be virtually impossible for the p hat not to be very close to P at that time. So let's just assume that it is P. And we'll plug in our 10,000 trials. And point 4, probability of success, 4,000 wins. And 6,000 losses. Do the same thing as above. 4,000 minus 6,000. He's now in the hole $2,000. As you can see, according to the law of large numbers, the results of having a negative expectation in your game will only increase the losses that you sustain over time. So the casino, they want to design the games this way. Slot machines, computerized games, they want it to be weighted in their favor and not weighted toward the player. It's how they stay in business. So they know that the more people play, the more likely it is that the people are going to lose the money, and then the casino is going to earn the money.